Okay, so we're going to be going over, why does it say 10? Sorry. We're going to be going over Unit 1, oh no, Unit 5, Lesson 1. And this is the first lesson in our chapters of geometry. So I'm going to tell you the biggest piece of advice that I could give you for these chapters is number one, be patient with yourself, because it does take a different way of thinking for geometry. And then number two, I just kind of want you to think about you being a detective the whole time. Just be a detective. So I'm going to start teaching on this lesson, which is called How Do You Know That? So it's called, and this is a good question. Okay. So keep in mind this question because it's going to help you understand. So it says, the following students have observed the sum of two odd numbers seems to always be an even number, but their peers aren't convinced this is always the case. Each student has given a different explanation as to why they think the claim is correct. Write at least two things you notice and one thing you wonder about the following explanations. So I'm going to have you pause the video here. I'm going to pause it as well. And I want you to read through these and tell me two things that you see and notice. Again, one of the biggest skills that you're going to develop in the geometry chapters is your observation skills, like to the point where you're going to notice a lot. Like there's so many things that you're now noticing. So student 1, 2, 3, and 4, in all of them, maybe you notice something about student 3 and 1. Maybe you wonder about what, like, you don't quite understand 4. So give me a couple of thoughts on that. Okay, so there's a bunch of different answers you could have said. Whenever I ask you to notice things and wonder, there's not a right answer. There's nothing that I wanted you to notice. This skill of noticing and wondering is actually a really good human skill, not just a math skill. So I'm just going to read them through. It says, I heard one of my teachers say that the sum of two odd numbers is always even, and she knows everything about math. Student 2 says, I tried a lot of examples and I found that the sum of two odd numbers is always even. For example, 3 plus 5 is 8. 19 plus 21 is 40. Student 3 says, I know that an odd number of objects can be paired together in groups of 2, with one object being left over. If I combine two such groups together, the extra ones will also pair together, so the sum of two odd numbers will always be even. I drew the following diagram to show what you were thinking. 5.1, hun. Okay, so student 4 says, since an odd number is one more than an even number, I can represent odd numbers like this: 2m plus 1 or 2n plus 1. If I add those two numbers together, I get this: 2m plus 1 plus 2n plus 1. And then I get 2m plus 2n plus 2. And then this last one says 2 times something. So don't worry about this, student. If you do not think like this, student, I'm going to just be honest with you. My seniors, they are comfortable enough that I can get them to think like this, but they don't start off thinking like this. Okay. So the last expression, 2 times something, is even because 2 times something. It is even because it's 2 times something. So the sum of two odd numbers is always even. So several of you have this, kind of like a little bit of this, maybe a little bit of this, some of this, but a lot of this. So pictorially, I really like this drawing. So I just wanted to review that. So today what we're going to do is examine ways, I don't know why this is tiny, examine ways of knowing that the sum of angles in a triangle is 180 degrees. This is something that you guys have known since, I don't know, 6th, maybe 5th grade. I'm not sure. So if you don't remember that, that's not a problem. I'm telling you now, so that'll be in the front of your brain. It says, examine ways of knowing the sum of angles in a triangle is 180. How do I know something is true? Are there different ways that I know or accept things to be true? When I notice a pattern in examples or through experimentation, how can I convince myself that my conjecture is always true? So this right here is really important. So in the land of being a human, not just math, right? You notice patterns all the time. And then when you test those patterns, When are you able to convince yourself that now it's not just a pattern I'm noticing, this is a truth, right? So the word conjecture means like kind of like an observation, and you made a statement about it, and now you're seeing if it's true. So it says, regardless of the shape or size of a triangle, is there a characteristic that is the same for all triangles in addition to being a three-sided polygon? All right, so more reading. You may know that the sum of the interior angles of a triangle is 180. If you didn't, you do now. But an important question to ask yourself is, how do I know that? So again, this question is very important. So questions that could arise is, how do I know that, let's see, how do I know that, what could I ask? How do I know that it's raining? And so some of you are like, well, I look outside and the ground is wet and I can kind of see like the drops dripping and so on and so forth. So you kind of have some kind of like evidence. So it says, we know a lot of things because we accept it on authority. So that's like student number 1. My teacher told me. We believe what other people tell us. Things such as the distance from the Earth to the sun is 93,020,000 miles, or the population of the United States is growing about 1% per year. So other people have told us these things. I didn't measure how far the sun is, right? I have never done that. So other things are just defined to be so, such as the fact that there are 5,280 feet in a mile. Some things we accept as true based on experience or repeated experiments, such as the sun always rises in the east, or I get grounded every time I say stay out after midnight. What? And then in math, we have more formal ways of deciding something is true. So we're going to do a couple of experiments. Some of them is like, if you have these tools, then we're going to go for them. If not, then I'm going to show you them pretending that my screen is a piece of paper. So I'm going to give you a second to collect some stuff. You just need a piece of paper. So it says, cut out several different triangles of different sizes and shapes. For each triangle, tear off the 3 corners, the angles, and arrange the vertices so they meet at a single point, with the edges of the angles touching each other like a piece of a puzzle. Okay, so I'm going to pause this, and I'm going to ask you to grab a piece of paper, and then I'll show you what they want you to do. So here's your triangle that they're asking you to do. And it doesn't matter which triangle you draw. If you are drawing a different triangle than my triangle, you should be fine. Okay. You can, yeah, if you have scissors, that'd be great. If not, you can fold and tear that. You can use that as well. So what you're going to do is you're going to tear these. There it is. You're going to tear the corners of your, this is me tearing. Isn't this such a good tearing? I know you guys are like, be quiet, Miss Johnson. Okay. So you're going to take these 3 corners, you're going to tear them off, and then you're going to arrange them so that these points are called vertices. These vertices line up together. Okay. You're going to grab these vertices and line them up together. So I'm going to pause really quick, and then I'm going to have you do that. Okay. So what you have, yes, you're good. So the very first thing that I want to show you is a couple of things. And this is going to be a long explanation, but this is kind of where I wanted you to go. So ignore me using these tools. These tools are just, if we were in class, I'd be able to do the same thing with pieces of paper in front of you. But because we're, online, it looks a little bit different. So the very first thing is I asked you guys to build a triangle. So I'm going to do that. And it doesn't, your triangle doesn't have to look like mine. Okay. Let's see if I can snap those in. There it goes. Okay. And I should have just used a triangle. Okay. So what happens is I asked you guys, I want you to tear this piece of paper here and tear this piece of paper here and put them up here and see if you notice anything. So did anybody do that? And what did you notice? Did you notice anything? Okay. So if I could tear this right here and put it up here, it would kind of look like this, right? So it looks like this angle here, it says it's 65 degrees. Do you guys all see that? So I'm going to make another angle up here so that it's 65 degrees. And I'm going to try to be perfect about it. Can you all just pretend that I just drew this, like I tore this and I put it up here? And let me just go this way. Does everybody see my this tearing here is this angle? Is everybody okay with that? The shape, this part here, we're not going to do anything. You could just leave it. So does everybody see that? If I did the same thing to this side, and I used any angle. Oh, I'm doing segments. I wanted to do angles. So here's my angle. And do you guys all see that it's 33 degrees? So if I do that up here, does anybody notice anything? I want it to be 33 degrees. Does anybody notice anything? What do you see? Yeah, very good. Someone said, hey, Miss Johnson, is that 180 degrees? Now, how did this person know there was 180 degrees? Right? Did this person measure it? Did they measure? Is that what they did? No. So they just knew that, and this is, if you don't remember it, it's okay. But they remembered that a line always measures to be 180 degrees. For those of you who don't believe me, I'm going to use this angle tool to measure right here. And if you do add these up, now, again, it's not perfect because I can't measure it perfectly. But if I think I missed just a little bit. But if you do add these up, it's supposed to be 180 degrees. Oh, awesome. Yes. So that's how you can kind of prove that it's 180 degrees. Ms. Johnson, why is this a little bit off? I think it's because how I measured it or how it's being rounded. So for example, if this one is like really like 31.7 or 33.7 or 32.7, they're going to round up, right? Or round down. And so now we've got rounded numbers, right? So it's supposed to be exactly 180 degrees. And the three numbers, yes. So these three, because these three add up to 180, that means that these angles in here, triangles, angles, always will add up to 180 degrees. Does that make sense? So this is the why behind that's true. Okay, this is the why behind it's true. Okay, so let's type out some answers here. It says, what does this experiment reveal about the sum of the interior angles of a triangle? What did you guys tell me? That they add up to what? How would you put that in your words so that you can remember? How would you put that in your words so that you can remember? Excuse me. Very good. Someone said they said the angles of a triangle will add up to 180 degrees. So you guys probably said the same thing. You're like, really, Ms. Johnson? That's all you wanted us to write? Yeah. I'm going to fix the language just a little bit so we can be a little bit more precise. So I'm going to make this bigger in Ms. Johnson's font so that you guys can find it on our notes page. So the first thing I would say, it's technically the measures of the angles of a triangle will add up to 180 degrees. Now that doesn't matter if your triangle looked like this or not like this. And actually, I have a better idea to prove that. Hold on. So if I go back here and let me clear it. Can I clear this? And I should have used this tool in the very beginning. This is a polygon tool, and you can make any triangle that you want. So I made this one. I'm going to make, say, like this one. Yeah. Oops. Okay. So I made this one, and I can add these up to be 180 degrees no matter what, actually. So really quickly, just so we can spend some time on this. And again, it's going to be, actually, let me undo that. Let me fix it. I'm going to fix it how I want it to be so that the way, there, that's better. Okay, so when I measure this angle here, that's 24 degrees. It should be the same as this one here, right? And it is 24 degrees. And then same goes with this one. And I want to show you this because this tool, this is where technology is better than, this is where technology is better than pencil and paper. Does that actually, okay, this one actually adds up to everything. So look at this kind of cool thing. So I could grab this guy and change it. And what do you guys notice when I changed the, can you just look at this number? Don't look at every number, just look at this number. As I change this here, this is 46. What else happened? What else do you see happening? Very good. All of these angles are changing. Specifically, who else is matching this 46? This guy, right? But no matter what, these three are stuck being at 180 because these three are being stuck at adding to 180. So does everybody see that? So this is a really cool tool that Desmos offers. I can grab these and change them. Do you want my triangle to look all like little and short? Do you want him to be tall like an isosceles? How would you like, do you want him to be kind of like a, let's see if I can get him to be an equilateral triangle. Let's see. Go outward. There you go. So this is the triangle that's famous in kindergarten, right? The reason why I call it famous in kindergarten is because this is the triangle that they'll see. And then they'll see, actually, they don't see that one. They see this one. Hold on. Let me see if I can get this. They see this one. Let's see this one. There you go. Dude, this is like taking too much time, Miss Johnson. There you go. So they see this one that he's sitting flat here. And then when they show them where he's like upside down, people are like, he's an upside down triangle. It's just a triangle, right? I don't call you upside down because you're, doing a handstand. So just kind of keep this thing in mind that no matter what, these will always add up to 180 degrees. Right here, 52 plus 94 plus 35. Yeah, that's 180. Okay, wait. What about here? 137 plus 22 is 159. Plus 21 is 180. So no matter how I move this thing, let's see if I can move this guy down here. It'll always add up to 180. Okay, that's true. Okay. There you go. So since you and your classmate has performed this experiment with several different triangles, does it guarantee that we will observe the same result in the triangle? Now, because we as a class tested that many, technically it only works for the ones that we've tested. Even though, hey, Ms. Johnson, you tested a lot of them when you were moving those triangles around. Doesn't that count? Yeah. But literally you would want to test all of them for something to be true. Yeah, we don't. We're just talking about the ones inside the triangle. The 80, the 54, and the 46. Really good question. Really, really good question. Very good. All right, let's move on, guys. So this one is experiment 2. Perhaps a different experiment will be more convincing. Cut out another triangle and then trace it onto a piece of paper. It'll be helpful to have color-coded each vertex of the triangle. As the new image of the triangles are producing this experiment, color code the corresponding angles in the same color. So locate the midpoints of each side of your triangle by folding the vertices that form endpoints onto each other. So you're taking your triangle, right? And you're taking like the side of your triangle and you're folding it so that your vertices are together, so that you made two congruent segments. So like these two now, like you see how that is? These two are congruent, right? So rotate your triangle 180 degrees about the midpoint of one of its sides, and then trace the triangle onto the colored paper. Now rotate this image triangle 180 degrees about the midpoint of the other two sides. Trace the new triangle onto your paper and color code the new segment. So this is a lot. I'm going to show you what to do in just a second. So just know we're going to try to find a different way to prove that in a triangle, no matter how my triangle looks, it's always going to be 180 degrees. Okay. So let me show you what I want. I'll be right back. Okay. So we're back and we want to go over the takeaways. So there was a couple ways of knowing that we talked about, and each of the four students kind of represented it, right? So the first way of knowing was like accepting it on authority. Let me just make this different right now. So it's accepting it on authority was the first student who kind of was like, well, because my teacher told me. Remember? And then the next way of wait, hold on a second. Let me highlight this. So the first way is accepting it on authority. So now you don't have to believe that I told you that your triangle sum add up to 180. You actually saw it, right? You saw an experiment of it. The next way is you know it's true because of you tried it out, tried multiple examples. So that was when we looked at the triangle and we moved the triangle around and we had a bunch of different angles and it actually worked, right? 1 second. Okay. The third one is making an argument based on a diagram. And do you remember I said I really like this diagram because it kind of shows what happens to the odd one out, right? So the next one is making an argument based on a diagram or representation. So that's like a drawing, a graph, or something like that. And the last one is making an argument based on other statements that have already been proven true. So I'm going to say that again. So making, and that was the last one that the student for that you guys were like, whoa, do I have to be like this? An argument based on previously proved statements and logical ways of reasoning. So what does this mean, Ms. Johnson? What's this last one mean? So if I said, let me think about one. Like, let's pretend I say that every time that you guys answer a question in class, I'm going to give you a participation point. Okay. So then I say, hey, let's see, if you have 7 participation points, I'm going to give you a free quiz question. So then we notice that, I don't know, say John gets a free question on a quiz. So because we know that the only way to get participation points is this way, do you guys all see how that logically goes? So this student, that student 4, he based it on the fact that we knew that even numbers are like numbers, and then odd numbers are numbers one more than that. You guys remember that? Okay, so let's see. These ways of knowing showed up in our work today when you conjectured about the thing, like the triangles. One of you said, oh, I noticed the straight line. One of you said, oh, that means it's 180. Remember this thing over here? I noticed the straight line, Miss Johnson. That must mean that this is 180, which then means that this is 180. So the way that you use this one, make an argument based on a previous statement that was proven, was you guys all told me, oh, this line adds up to 180. And because this line adds up to 180, And the parts are here. The 46 is here. The 80, imagine him jumping up and then dancing right over to here. And this guy coming over here as well. Then that means these three add up to 180. Do you see how you did that one? That's what you did in this one. Okay. And then, so now that I know that it's true, and then don't worry about this part. Okay. So there's two types of reasonings that I want you to think about. Okay. Have you ever heard of anybody say, like, there's deductive reasoning? Have you heard this term yet? Not yet. So, like, inductive reasoning is based on making conjectures based on experiments on several different examples. Yeah, right? So I'm learning, like, this is how little children learn, right? So they, I don't know, what would they do? What do little children do? They are like, oh, I wonder what this is, and they'll touch it, and they'll be like, oh, this is okay to touch, or this is not okay to touch. So then eventually they get to the point where they learn what to and what not to touch, right? So no one's teaching them and saying, okay, the reason why you shouldn't touch the stove is because it's hot. Like, I'm sure parents are telling children not to touch the stove, but because, yeah, exactly, because they're very curious, they touch things. And the child only needs to touch the stove once to be like, yikes, that hurts. So no one actually told them, right? No one told them, like, the reason why you shouldn't touch this is because it's going to burn your cute little finger. And when it burns your cute little finger, it's going to get a blister. No one explained that. They just understood, like, ow, that hurts. So they learned by making conjectures based on experiments across several examples. Does that make sense? So as a mom, I will say that I learned after, I know, right? I learned, like, there were several things that my children did not like. Like, I remember my daughter, I know this is a really weird example, but like, I made this guacamole and I like garlic a lot. So one time, she had some and she was not okay. Like, she was like sticking her tongue out and she was like upset. She was crying. And I was like, I wonder if it's the garlic in the guacamole kind of thing. So you will learn as you walk around through examples what to and not to do, right? So hopefully you don't keep touching the hot stove and being like, I wonder if it's going to hurt this time. Ow, right? I wonder, ow, right? Hopefully you learned it after maybe the first time, right? Some of you, I know you've told me, no, I needed more. Deductive reasoning is different. I'm not learning from a lot of examples, right? I'm learning from, like, facts or other things that are true. So if I say, oh, because I know this, like, I don't know, because here's an example. Because I want to find out 5 times 5, for example. And I don't know 5 times 5, but I know 5 times 4. So because I know 5 times 4, and 5 times 5 is 1 more 5, that means that I just need to add 1 more 5 to it. See, that's not on examples. That's based on properties. That's based on facts that I already learned. Does that make sense? You guys okay with that? So in this, like, for this chapter, we're going to be using lots of properties, definitions, postulates, and theorems. Just know that all of these things, you will slowly learn what each of them are. I've done this thing where I tell everybody what each of these things are, and then it doesn't make sense until I show you what one of them means. You're comfortable with definitions because you know what definitions are, right? Definitions are like what the thing means or how a thing is described, right? So the only other thing that I wanted to tell you, no, that's it. So I've been encouraging you all to read this. So I'm going to read this for you to be an example. So in this lesson, we explored different ways of knowing something is true, such as basing our knowledge on being told something by someone in authority, basing our knowledge on experimentation or reasoning with a diagram, We examined these ways of knowing the context or justifying how we know the sum of the angles of a triangle is 180. So I'm going to give you a couple of examples between inductive and deductive, and you guys vote. Are we talking about inductive or are we talking about deductive? Okay. So let's say you think that Miss Johnson wears black every single day. Would you learn that from inductive or deductive reasoning? Could you prove that, I guess, through inductive or deductive reasoning? What do you think? Miss Johnson wears black every day. Uh-oh. What do you think? In the chat. Come on, let's go. Yeah, very good. It is inductive reasoning. It's not deductive because like, you can't prove that I wear black every day based on a definition. Like, there's no definition out there that says Miss Johnson wears black every day or Miss Johnson doesn't wear black every day, right? There's no property out there that says Miss Johnson wears black every day, right? There's no postulate that says if the lady is Miss Johnson, then she wears black every day. There's none of these, okay? All right, what about this one? If it's raining outside, Miss Johnson is gonna wear rain boots. If it's raining outside, Miss Johnson is gonna wear rain boots and have an umbrella. I'll add that. Inductive or deductive? Remember, deductive is only using properties, definitions, postulates, or theorems. Ouch. Yeah, it is inductive. Very good. So what about if this month is February, which it is, right? If this month is February, then next month, oh my gosh, next month must be March. If this month is February, then next month must be March. What do you think? Yeah, it is deductive because someone says you lost me. Okay, so is there a definition, a rule out there that we've all agreed on that if this is February, then next month is March? Yeah, right. It's called the calendar. Okay, very good. What about this one? So since I see you driving, no, I'll say it differently. Um, one of you come in the next time we have class and you're like, I got my license. Would it be inductive reasoning or deductive reasoning that um, I can conclude that you are 16 years old? Is it inductive reasoning or deductive reasoning? Did I have to go through a lot of examples to test to see if you were 16? Or is there some rule out there that tells me that you have to be 16 in order to get your license? Or at least 16, I guess I should say. Very good. This is deductive, right? There's a law out there that says if you're this many years old, or whatever. I don't even know if it's a law. I don't think it's a law. There's a rule out there that in California, in order to drive, you have to be at least 16 years old to drive with a license, right? You can get your permit when you're 15 and a half, right? But in order to drive with a license, you have to be 16. Okay, what's another one I could think of? I think we'll end it there. Very good, very good.